To really understand climate change and the ways we can make a difference, it's important to kind of understand who the big players are. Around the world, which countries are doing the best, which are doing the worst. Looking just at the United States, we can look at a state-by-state level. We can look at the global level, what are the trends? And so this lecture is going to take a look at just trends in greenhouse gases. Yes, there's going to be a lot of graphs, but again, graphs are such a great way to view a lot of data, excuse me, a great way to view a lot of data at once. So let's take a look. So this graph is kind of a famous graph. It's referred to as the hockey stick graph, where you kind of have this low part and then it goes immediately up, kind of like a hockey stick. This is looking at carbon dioxide emissions for the past 800,000 years. And you can see, for the most part, it's fluctuating. And one of the largest counter-arguments of climate change is that it's part of a natural cycle. And while that's not necessarily untrue, the part of the natural cycle only is going between 200 and 300 parts per million. So this ppm that you're seeing over here, this is again that parts per million. And what this is saying, if there's 1 million molecules, this is how many of those molecules are carbon dioxide. So if it's 200 ppm, that's saying of 1 million air particles, 200 of them are carbon dioxide. Now that doesn't sound like a lot, and it's not. But remember that these greenhouse gases are really good at their job. At 200 parts per million, we're still trapping a lot of heat on Earth. In fact, if we were to plot when ice ages were, every time carbon dioxide is below this black line, we were in an ice age. So 200 parts per million means ice age. About 250 parts per million is when we start warming up and we're out of an ice age. So there's actually a very tight relationship between greenhouse gas emissions and ice ages, which should make sense. Greenhouse gases are trapping heat. The more you have, the warmer Earth is. When you have less, then there's less heat and we're in an ice age. Now the rest of this graph, now it looks crazy high at this 900 parts per million. We are not there. We're not quite close there. This is just if we were to estimate, if we were doing not good, if we weren't, really lowering our emissions, here's what it might look like in the year 2100. But we're not there. Where we are, though, is as of the making of this video, we are currently at 414 parts per million. So much higher than it's been in the past. Yes, we have a natural cycle, you can see that here, but it ranges from 200 and 300 parts per million, and we're much higher than that, right? We're over 100 parts per million higher than the highest we've seen in the recent past. So this is where the concern is. In the past, we knew, okay, this is what to expect here, here's what to expect here. We don't know what to expect. This level is unprecedented, and it's only rising every single year, which we'll talk more about in a little bit. Before moving on to the next slide, what I want to do is kind of talk about how long it's been taking to change. Let's use green. So my question to you is, in the past, how long did it take to increase 100 parts per million? Because this is the other issue with climate change, is that you can see here on the far right side, this is nearly a vertical line. It's not a smooth slope up or a smooth slope down, it's straight up. And the next slide is going to talk a little bit more about that. But we'll ignore present day. Let's just look at the past. How long has it taken? So I'm going to purposely choose maybe the point that looks the most, quick or narrow. So let's use this point right here. We're going to call this 300. And here's its low point. We're calling this 200. Again, these are estimates, but again, I just want to know how long did it take to increase 100 parts per million. So I'm going to trace this down, probably very poorly. That actually wasn't too bad. And oh, that's bad. Let's trace down the 300 line. So this right here represents the number of years it took for the environment to naturally increase in carbon dioxide. I say naturally in the sense that humans are not impacting this right now. And so if we take a look at this, okay, between two numbers is 100,000. Between two lines it's 50,000. And this is what, maybe a third of that? So I would say in the past, it has taken 15 to 20,000 years to increase 100 parts per million. So 15 to 20,000 years is taken to increase in carbon dioxide, increasing by 100 part per million. Keep that in mind. We're going to come back to this number. Last thing I want to point out is that if you look at this timeline, you maybe have thought of where we got this data from. Like, humans evolved here. Homo sapiens came into the picture around 200,000 years ago. We have not been recording carbon dioxide since we evolved. There were no humans around in 800,000 years ago. Where we get this information from is from ice cores. So if we look at Antarctica, Antarctica has been there for like ever. Antarctica is just layer and layer of ice. Every year, more and more ice gets added. And what they do is they take this drill and they drill out this core of ice. I mean, and this core can be hundreds of feet long. These are very, very long cores. Now, if you think about an ice cube, when an ice cube freezes and you take a look at that ice cube, you see all these little air bubbles in it. Well, in those air bubbles are air. It's the air from when that ice froze. And so what we can do is we can look at different parts of the ice core. Up here at the top is recent. At the bottom is going to be very old ice. Through some other science, we can date when that ice was formed. And what we can do is we take a very fine needle and we literally stab the air bubbles and suck the air out of those air bubbles. And then we can measure not just carbon dioxide, we can measure oxygen, we can measure hydrogen and argon and neon. We can measure all of these different things that were in those air bubbles. And it gives us a little picture and a little insight into what our atmosphere looked like at that time spot. So that's how we have all this data. So I don't want you to think this was just made up or whatever. We measured this from air from those time periods, which is kind of impressive that science enables us to do that. So it's cool to kind of see what's happening in the past, but let's take a closer look at what's happening right now. So a couple different things to dissect. So let's look at the title. It says Atmospheric Carbon Dioxide at Mauna Loa Observatory. On our x-axis is the year. You notice that we are looking at 1960 to 2020. 1960 is when we first started directly measuring carbon dioxide in our atmosphere. And specifically, this graph is looking at the direct measurements from Mauna Loa. Although you might not know where Mauna Loa is, maybe you've never heard of it, maybe the word or the style looks familiar. This is on Hawaii. And the reason this matters is because Hawaii is in the middle of the Pacific Ocean. It is very far from any major city. Although people live on Hawaii, you don't have tons and tons of industries, tons of cars. It's fairly unpopulated as compared to other places in the world. And so by putting this observatory on Mauna Loa, in Hawaii, in the middle of nowhere, in the middle of the ocean, that whatever carbon dioxide they're measuring is not getting biased. It's not artificially higher because of cities or air pollution or vehicle pollution. So we feel very confident that the trends we see here is really what's going on in the environment, and it's not just here's what's happening in Hawaii, here's what's happening New York City or Los Angeles. No, this is what's happening in the middle of nowhere, so more likely to be accurate. On the left-hand side, we do have parts per million. Again, ppm. This is how we measure gases in our atmosphere. Now, if you look at this, you're like, well, this isn't a straight vertical line. Well, it's because we've stretched it out. Instead of looking at 800,000 years, we're currently looking at 60 years. So what I'd like to do is I'd like to take a moment to kind of do the same analysis we did before. How long does it take for carbon dioxide to increase 100 parts per million? And let's compare that. So in the past, we said it took 15 to 20,000 years. Now, how about now? How long has it taken us recently? During our lifetimes, during your parents' and grandparents' lifetimes, how long has it taken us to increase 100 parts per million? So I'll start down here. We'll start at the lowest part of this graph. So this is probably, brain farting right now. This is actually probably like right at 315 is the very first value. We know the most recent value is 414. For simplicity's sake, I'm going to say 415. So essentially this graph represents a difference of 100 parts per million. We went from 315 to 415. Now the question is, how long did it take that? Now again, I like rounding, so we're going to say that this 315 was in 1960. And we're going to say that this 415 is in 2020. So that's 1960 to 2020, which is 60 years. 60 years. In the past, it took 15,000 to 20,000 years to do what we've done in 60. And so the concern isn't just, oh, carbon dioxide's higher in the atmosphere. While that is a concern, the second concern is we are increasing it so freaking fast compared to what has happened in the past. And that's going to present its own set of issues. Organisms can evolve. Bacteria, fungi, plants, animals, they can evolve. But they need time to, right? If an elephant's lifespan is 70 years and we've just increased this in 60 years, they don't have the time to evolve to the changing environment in that time span. And this is where a big issue is. Sure, we can adapt to hotter temperatures, but are we going to be able to adapt fast enough to these warmer temperatures? And that's where the main concern is. Another thing I want to point out, this graph and the next graph that's about to come up, this is from NOAA. NOAA is a government organization, a U.S. government organization. The United States is kind of notorious for not doing a lot when it comes to preventing climate change or fighting climate change. And the fact that it's still the U.S. government that is funding this research, that is displaying this data, that is publishing this data around the world, this should tell us something. We can argue all we want about stuff, but the federal government, who is kind of notorious for not being pro-climate change, is also the same organization who is providing the key data showing that climate change is happening. So this almost makes you just want to believe it even more. Like, hey, you guys disagree with it, but you're still publishing it anyway. It's probably because it's actually happening, right? And it's real. We can measure it. We can see it.